the blanket was right there. The blanket is right here, right? I'm busy in class. You can get it yourself. He wanted a blanket that was right next to him. I think he's feeling a bit lonely. So, let's keep going. So, keep going. So we've got, so right, this is 7 nodes in it. And it's the only way you can have 7 nodes in a tree of height 3. So this is a good example of that. It's something that has to be completely filled up, essentially. Now, what the heck is a complete tree? Well, it's perfect on the top. Like on this layer, but the next layer below it is filled up left to right. So it could potentially be perfect. But this is a complete tree. This is not. Nor is this, because there's a gap. Nor is this, because it's not filled left to right. In other words, it needs to be able to be transferred into a heap, into array like you would do with a heap, but without any gaps. Let's keep going.
Full and perfect.
Sorry?
The full and perfect, what's the difference?
Yes. Full and perfect were look different. All right.
You said that they're the same?
No, full and perfect are different. Full means you have either 0 children or no children. So you can't, so all perfect trees are full and complete, but not all full trees are perfect. All right. So for instance, this is full and perfect, but this is also full. Everybody has either zero children, like this guy, or everybody has 2 children. Make sense?
Yeah, got it.
All right. Now let's go and try this one. All right. So next, we need to draw a binary search tree that forms after we insert the following nodes. 42, 10, then 50, then 12 is less than 42, greater than 10, so 12 goes here, then 17, then 80, then negative 12 is less than everything, so it goes all the way to the left. Okay, and now 100 is bigger than everything else. The 96 is like greater than this, greater than this, greater than this, less than this. And then 105 is greater than that. 86 is greater than this, less than this, less than this, so 86. And then 72 is less than. Okay. That's how we would add these things. Now, what about the removal? Using the previous tree, we'll draw what happens if you remove the following. So I'm going to remove these step by step. Removing 17, so removing 42. To define 42, to remove 42, what we do, because it's got 2 children, we go 1 to the right, left, and all the way to the right. So I'm going to delete 17 by moving it, or I'm going to delete 42 by replacing it with its next in order predecessor. 17. Because that was the smallest, it was the biggest item that was smaller than that. So it was best suited to be the root. Okay, next let's remove 12. Well, 12 is just a child is just a node without any children, so it just deletes just fine. Okay, Next, 17. 17 is the root, so we need to go and find the biggest thing that is smaller than 17. That means go one to the left and all the way to right. So delete that. It has one child, so we adopt that child as our own. And since we were deleting 17, we replace it with what was going to get removed, which is 10, right? So technically what I should do is say, hey, 10, replace this 10. And remove the old 10. Well, laser, you'll need to hold on a second. And then finally, removing 96. Again, 96 removing, it has one child to remove. So sorry, removing 96 means you have to take care of adopting one child. So there you go. And that's what happens when we do our add or remove operations in a binary search tree. All right. Post order, pre-order, traversals. All right. Which of the following is a pre-order of a traversal of a binary search tree with trees left and right? All right. So first, to do pre-order traversal, that means we want to handle the root first, and then the left, and then the right. So that would be B. And then what is the post-order traversal? That would be do the left our children, then myself. So that'd be C. All right. So I'm going to, before I move on, I'm going to get laser situated to try to reduce any interruptions, and then we will continue with the heaps, and then we'll get on with the coding. The Huffman coding is not going to be on the exam during the summer. There's just not enough time for it. So. All right. Most have drive for desktop. Share screen. So let's go ahead. Draw the min heap that forms after inserting the integers. So to do this one, right? First, let me get my pen up. Annotate. All right. Draw the minimum heap that forms after inserting the following integers. Okay. 8 inserted first, and you could ignore the underlying array. So what we'll do to build a min heap is that basically with minimum heaps, the smallest item always bubbles to the top. So 8. Okay. And then we always add. When we add into the next location so that the tree is always, so that the heap is always a complete tree. So 10. So this 10 so 10 is heavier than 8, so it's perfectly fine there. 50 is heavier than 8, so it's perfectly fine there. 20 is heavier than 10, so it's perfectly fine there. 1 is lighter than 10, so we need to swap those two, right? And see how I'm always putting something such that what I have is always complete. So swap 1 and 10. Now 1 is less than 8, it's lighter than 8, so it needs to swap. It needs, the lighter item needs to bubble to the top, while the heavier item needs to sink down. Okay. Next. So we did 8, 10, 50, 21, and now 4 is less than 50. So 4 is less than 50, so we need to swap those two. Okay. 4 is less than 50. I just found something out I can do. So 4 goes here. And 50 goes here. Okay, that was all terrible. And 50. So they've swapped. Now 4 is greater than 1. It is heavier than 1, so it's not going to bubble any further. Now we have 3. Okay, and now we go ahead and we swap those because 3 is lighter than 4 and 4 is heavier than 3, so they swap. Okay. So next, drawing the heap above, using the heap you drew above, draw the heap after removing the element twice. So let's go, so to delete, so we always delete an element from the top of the heap by doing that. And what we do when we delete an element is that we take the item from the last location and move it to that location and move it to the root, to the top of the heap. Now, the reason we do that is that, again, we always want to keep this heap complete. So deleting the thing at the top means that we have to move the thing that's the only node in the heap that would keep this a complete tree. However, now that we've kept it a complete tree, we have to swap things around because it's no longer a min heap. For it to be a min heap, every part of it needs to be a min heap. So that's why we kept swapping more than once. Okay, so 4 is not as heavy as 8, but it's heavier than 3. So 3 and 4 need to swap. It's that simple. And 4 can't be pushed down, and 4 basically isn't heavier than 50 or nothing, so it's done. Essentially. Okay. So next, we need to delete. If we're deleting twice, we're going to delete 3 next, which means moving 50 to the top. Now, in this case, 50 is heavier than both its children, right? So what do we do in this case? Well, we swap with the lighter child. The lightest item always should bubble to the top, so that's what we do. And there you go. So we've deleted 1 and 3, which are the 2 smallest items. What do you want to eat while you watch? Well, when you figure that out, let me know, Laser. I need to keep helping my class. So I am getting close to done with the exam, except we're now on the coding portion, which does take a bit more time. So this one says, hey, calculate the size of the tree without using the size method. Used to put it on an exam so I could get a gander of how well the students were doing. Now for the exam, right, you'll probably want a Java class BST, binary search tree, E, okay. Oh, I'm not going to use that. I'm just going to use public class E comparable. There we go. And really, and we don't actually need any more than just creating a node class. Public static, or rather private static class node E extends really not on form tonight. Comparable E. And that has, the node will have a left a right, and a E item. Node, and now the constructor, public node, E, what is public E item? To store the item, that's all we need for this. So now let's go ahead and do public int size, and given the root of a tree or subtree. So node E root. Okay, so to do this one, what do we have to do? We have to iterate through. Basically, we have to figure out what all the items in the tree are. So how do we do this? Well, let's think about this for a second. What is our base case? Our base case is the empty set. How big is this tree made up of no nodes? Well, it's made up of 0 nodes. So I would definitely say that, hey, if root equals null, return 0. Now, if it's not null, so again, essentially we're dealing with two situations here. Either the tree we're dealing with is null, right? Let this be the null tree. Or we're dealing with this situation over here, which is that we've got a node with an unknown left subtree and an unknown right subtree. Now, what's the height? Sorry, what's the size of this tree, total tree? Well, it'd be 1 plus however big this is, plus however big this one is. Make sense? So we can just, again, do nice and easy recursion here. That looks like magic. Okay. Where I'm just going to say, hey, otherwise I'm going to, otherwise, and I can do this in one line, return 1 plus the size of root dot left plus the size of root dot right. This one is just unlucky and able to do it. Assuming I can type it without creating an underscore for some reason. This will take O of n time because, of course, it needs to tackle n nodes. Okay. Next is full. So I like this one because it ties together the theory and the practice where we have to figure that out. So let's figure out if the tree is full. It's slightly different because we have to consider a couple different possibilities. The easy possibilities, right? So public int, it doesn't matter if it's static or not. Public static. Again, it doesn't really matter. Public static Boolean is full. Node E. So I want to know, so given the root of a tree or subtree, I want to know is this tree full? Is this tree or subtree full? Okay. So let's look through base cases again. This is first off, this is a question I'll have to figure out for my textbook. If I've got a null tree, is that full? I'm inclined to say yes, because it says every node has to have either 0 or 2 nodes, children. And having no nodes, having no children, it seems to incline to me that basically something that is null is full. So if root equals null, return true. And I'll just simply put in a return false to quash everything, but we'll probably delete that later. Return false. Okay. So now what do we have to do? Oh, because it's static. Yeah. So I'm going to just remove that. Now I don't have to do that. Okay. If root is null, return true. Otherwise, what are my other conditions? The other conditions that let me know instantly whether something is a full tree. Well, if I have no children, that means true. No children is equal to I'm a full tree. If I have one or this, if I have only one child, that means it's false. However, if I'm over here with, in the case of having two children, that means they've got two subtrees, and I can't really tell anything about them. Like here, I've got a subtree as well, but I mean, it doesn't really matter because I only have one child. So the figuring out what's the contents in is a bit more difficult. So, okay. So let's go ahead and knock out those cases now. So clear. Okay. So let's go through the other cases. Else if I don't know, I don't need any ifs. Let's do else ifs because else if root dot left is null, but root dot right is not. So in other words, if we have a right node, but if we have a right child but not a left child, and now I can just simply copy this, copy paste, paste. And then just swap those over here. If I have a left child but not a right child, then it's also false. Else it depends. I mean, I have two children, so I'm a full tree, but it really depends on the contents of my children. So in that case, I would have to say return is full root dot left and is full root dot right. Okay. So there we go. Left and right. Okay. Any questions on the is full?
Professor,
Yes.
wouldn't the if you made the same type of a method for like perfect or sorry, a complete one, wouldn't it be way more difficult?
Yes, it would be. A complete one would definitely be way more difficult. The perfect wouldn't be a perfect because of the mathematical definition. It wouldn't be so difficult because what you'd have to do is calculate the size and calculate the height and then see if it fits the formula. Make sense?
Yep.
But for a but for the other one, you'd have to basically do a breadth first search, essentially, of some kind to figure that out for complete. That's the easiest way to do it. For perfect, you just figure out the height and you figure out the size and then figure out the formula there. If you try to think of it as like, oh, a perfect tree, it looks perfect and ideal. Well, you have to, that's less than helpful, unfortunately, for programming because it's hard to do. Okay. Got this puzzle. It's not big enough for the ring so that I can just toss it and it solves itself, which is annoying. And then as a result, it's harder to put back on. So fix it later. All right. So any questions on this one? This one is about the difficulty I would put on an exam because you want some raisins. I'm not going to give you raisins unattended, Laser, because we've got a dog. So I will give you. I can give you raisins later. Okay. Yeah. I'm the only one here because my wife is feeling ill, so I am just busy working on that. Okay. All right. So this one is above the difficulty I would give. Write a method which, given two trees or subtrees, returns whether or not the constants of the entire tree are identical. Tree A and tree, in other words, do these two things have the exact same data in the exact same way? In other words, are they not only does the structure match, and does the does the structure match and does the contents match? That's why I was figuring out why that came up, because I was hitting shift. I can't give you raisins because I don't trust you not to drop them, Laser. Raisins are toxic. Raisins are toxic for dogs to have because they're grapes, and grapes are toxic for dogs to have. I have a dog and I don't trust him not to drop it, and I can't exactly watch him eat his raisins right now. So, all right. So let me go through this question, and then I might try to take a small break just to see what I can solve. So okay, so first off, let's figure out base case. What's an easy way to know if these things are equal? Well, if they're both null, they're equal. If tree A is null and tree B is null, return true. They're equal, right? Very convenient, right? I'm going to assume that they're equal until proven otherwise over here. So just so I can quash this. Else, and I'll take this if, and I'm going to be copying it because now we're going to iterate through all four possible combinations of that. And else. So now if we have one tree equal to null, but the other one's not equal to null, then they can't be equal because that means one exists while the other one doesn't. Laser, I cannot give you raisins right now. Return false, return false. Okay. And now the final one to check if they're equal. Well, the structure is the same. Now we have to check if these two things are the same. So else if tree A dot I mean I could put this in the else, but I mean I just want to make this as linear as possible, as straight as possible. If tree A dot item dot equals if tree A dot item dot equal if these two items are not equal, first off. Right, so if they both exist, I can check their items against each other. And these three checks make sure that they're going to exist. But if they don't match, return false. They aren't equal. And now finally, we have to ensure that and now we'd have an else statement, but we can continue on out here if we want to, which is just simply saying that, hey, okay, so we have two nodes. They both exist and they have the same item stored in them. So now we need to figure out what about their subtrees. Well, they're equal if they're going to be, these two trees are going to be equal if their subtrees are now equal. So, so now, and again, I'll do this annoyingly in one line, return equals tree A dot left, tree B dot left, and now tree A dot right, tree B dot right. Do that. And there you go. That is our solution. Now it is getting hard for me to work because I have a child shouting, "I want raisins." But let me go ahead and handle the food issue for him. Excuse me. All right, that crisis has been reverted. He is happy with Bomba, which for those of you who don't know, those are Cheetos, but instead of cheese, they're peanut butter. Very tasty. More of an Israeli thing than anything else. So, sorry, just feel comfortable for a second. All right. So where were we? We were on. So any questions about the equal method?
Professor,
Yes.
the item part. So like, it checks each where you like put not tree A item equals tree B dot item. So it checks each item for a subtree.
It just checks the roots, right? So this is just checking the two roots.
Oh,
This-
I see. Okay.
It's just checking the item in the root. I really should have named those two things root A and root B. But whatever. Does that make sense now?
Yep. Thank you.
Okay, cool. All right, next question. Okay, so you're gonna get some variation of this on the exam, which is given right method which returns what characters occur in the string and how many times each occurs, right? And you want to use a map because trying to do it within it's one of those kind of problems where if you don't know maps, you kind of like stop short because you have no idea what to do. There's not really an easy way to solve it without maps. there's an efficient way, which is to use an array and assign ASCII value and assign each character their ASCII value. But but you're in Japan, so that becomes increasingly difficult because you're dealing with Unicode text as opposed to ASCII text, and yes, ASCII is a subset of Unicode. But programming languages used to not play nice with Japanese until UTF-8 came along and support for UTF-8 came along. So let me actually just see for a second. I'm gonna pause my sharing. Okay. So I'm gonna grab because I cannot type. I don't think I have my okay, so resume share. Let's see. Can I use that as a variable name? I use this. No, I cannot use that as a variable name, I do not think. But if I use, but I can use, oh, well, duh. Hold on a second. Okay, yeah, I can totally use it as a variable name now. So yeah, you can totally use the, because of UTF-8, you can totally use those things as Japanese in your variables, which may or may not be easier for you. Make sense? So, and as long as it's because of the way ASCII works. Each character, remember, your computer is dumb. It's a rock we zapped with lightning to trick into thinking. Okay, so all it knows is ones and zeros. It doesn't know any letters. All we've done is encode every single letter as a 1 and 0. Has this been explained to you or no? So I'm going to assume no. So just a tangent over here. Right. So over here, I'm going to go ahead and so I'm just going to take the character ko. Okay. To show you guys. Okay. Car. Ko is equal to. Right. I'm not being dumb. That is ko, right? Provided string.
Yeah, you're good.
Okay, cool. Okay, so now I threw it into a string, sorry, into characters, because of course it's a single character. So now what I can do now is I can in reality, these things are integers actually, right? I can actually do operations like this. Sout ko plus 1, okay? Which it will do something useless and it's going to print out something actually mildly useless over here, which is going to print out a number 1237 and 2. And this is because that smaller types lose, right? Which is that if you've got a bigger type, if you've got a smaller type, it gets converted into a bigger type. All right. So if I put plus 0, this is the Unicode value for ko. Basically, and A, the Latin letter A is like 97. So just, for reference there. So a lot of the early ones are like control characters and stuff, or things to make a computer beep. So anyway, what I can do is that if I say ko plus 1, but then I take this and then I say, no, that's not an integer. That's a character. I can then see what is the next thing in the table, which is go. So, and I better not continue any further, otherwise I'll embarrass myself. Because I've forgotten more Japanese than I've learned at this point, I think. I'm quite terrible at at least being disciplined enough to learn a language on my own. But anyway, but this means that essentially that because of this, you can use Japanese text. We can use Japanese text, and it makes it really hard because if you were just doing Latin text, you could just do, for this one, I could say, hey, we've got a 127 character array, or sorry, 128 character array for each of the ASCII values, but there's a lot of ASCII values if we're working with stuff in Japanese, so, or Chinese or Korean, because all that stuff is on the further end. Basically, in the modern world, that you got to use maps because we're going to be using funky symbols. Okay. Okay, so let's go. So what do we need to do? Well, we first need a map. So I'm going to go ahead and new hash map. Okay. And now I'm going to just do a for each loop for car. For every character in the word, 2-character array. So for every character in the character word to translate to character array, that way I can just go letter by letter. If out, so first off, return, before I forget, return out. If out dot contains key, if it has this already, then the new value. So if I've seen this before, that means the new time, the number of times I've seen it now should be put out dot. I'll go ahead and call this map just to be clear. So map. Okay, map dot put. C and then map dot get C +1. So I could split this up into multiple lines, by the way, where basically I could say int times seen is equal to map dot get, okay, C, and then times seen +1. And then else, if I have, otherwise that means I haven't seen it before. So I haven't seen it before, so this is the first time I've seen it. Make sense here? That's actually all you really need. We can be a bit more clever about this because there is a what we can do here, all right, is we can eliminate this if statement with a cool function that that Java has. Right, now we've seen, time seen, this isn't going to work if we haven't seen the character yet, okay? If we haven't seen this character, we're going to get a key error. But we have a cool function built into this, which is like get or default, which simply says, which we provided two arguments, which is C. And so we're going to get the value associated with C if it exists. But if it doesn't exist, instead it's going to be 0. So it's either going to be the number of times that we've seen it, if we've seen it, or it's going to give us 0. Make sense to everybody? So this shortens it by an entire if statement, which looks pretty cool. I took her out about an hour and a half ago. Doesn't matter if I got these headphones on. My hearing's pretty good. I'm so excited. I'm getting a new pair of headphones tomorrow. Specifically designed for doing like music orchestration, that kind of stuff.
Yeah, me too. Nice.
What kind of headphones are you getting?
Sony that released 3 weeks ago.
Oh, really? Nice. Yeah. I'm getting, I think it's a Bayer Dynamics, but it's specifically designed for orchestral mixing as opposed to listening.
Oh, I see.
One of those open back headphones and not for commuting. For commuting, for my commuting, I have the Google Pixel Buds, you know, the little wireless ones, because I like having essentially earplugs in public, but also not having these giant conspicuous things. So I like the portability of these devices, but I'm probably not going to get a replacement once they die because I prefer stuff that lasts. Like this one has lasted. These Bose headphones. But anyway, let's go ahead. Yeah, keep going. All right, I'm gonna skip.
Professor?
Yes, go ahead.
So like, you know how you use like a dot car array to dot car array, like mini like little helpful functions like that. Like, are you gonna give us hint that they exist? Because I wouldn't have known unless you used it right now.
Oh, I've used that a couple of times, but I mean, if you didn't use that, if you didn't know how to do that, you didn't need to use a for each loop. I could just simply do a for, right? You could have done stuff like this, for in, and it would just been just slightly slower, which is doing a for I in word.length, right? You got to iterate over all the characters, right? So if you didn't want to, so if you didn't know how to use a for each loop like that, then you just didn't simply say char c is equal to word dot get car at I, right? Does that make sense?
Okay, thank you.
Right. So everything has alternates and ways of doing things. But I've used the to character array a couple times because for some, and this is a horrible design choice by Java, in my opinion. For some reason, you cannot iterate over a string. You can do that in Python. Love me my Python. But the minute you try to do it in Java, it gives you an error because strings aren't iterable. They don't have an iterator. So frustrating. So I converted into an array there, which is annoying. Okay, so I'm not going to go. So you can try the next one if you want. This is more relevant for doing the homework that's due. But let's talk about the analysis, because I do want to give you some time to work on the hangman game. My hand is just stinging from all the writing. The summer 2 class is having their exam review today as well. So I've been doing a lot of lecturing today, which, you know, I'm used to doing, but just don't like writing so much. Painful. What are collisions in hash tables? Why do they occur and how are they handled? So collisions in hash tables, they occur. So a collision is when two keys try to occupy the same index. This occurs because the space of possible keys is infinite, but the number of indices that are available in a hash table are finite. Does that make sense? You have more keys than spaces that can be fit, right? Are you all familiar with the pigeonhole principle?
Yes, sir.
Okay, so it's just a pigeonhole principle, right? The pigeonhole principle states that if you've got more pigeons than pigeonholes, right, then two pigeons are going to end up sharing a space and being very unhappy. Actually, I don't think the pigeonhole principle states anything about the temperament of the pigeons, but the point still stands. The point being is that there are vastly more keys than there are indices. So we have to have a way to resolve them. We can resolve that. We've learned there you can resolve them in any number of ways. We learned two categories of ways of doing this in the class. One is open addressing, and we learned two variations of open addressing. So the open addressing simply says, if my space is taken, I'm going to look for the next available space. So all the variations of open addressing is just simply like, how do we define next? Open addressing with linear probing defines the next available space as the space I would like to go as like literally the next space. So I will be, so look 1 over, then 2, then 3, then 4, then 5 spaces from the initial point. So in other words, if my index that I'm trying to go into is I, then I'm going to try to go into I plus 1, then I plus 2, then I plus 3, then I plus 4, and so on and so forth. Make sense? Right. So what the other way we learned for that is quadratic probing, which defines next as if I'm going to look 1 squared away from my initial space, then 2 squared, then 3 squared, then 4 squared. So it's quadratic, where we're looking at a number squared. Now, the reason you might want to do that is that it leaves less, is that it creates bigger gaps so there's less clumps for your mama will be back in soon, laser. There's less clumps for you to suffer for your array to deal with, and it's going to suffer less possibly. But the computation now requires an additional multiplication operation, which can, from a very technical standpoint, is slower. But there's an entire other category we learned, which is chaining, which simply says each space, each index is not actually a slot for a single item. It's actually a linked list. And so when there's a collision, we just add it to the end of a linked list and define something at that spot. We iterate through the linked list, but we do our best to keep the linked lists below a constant length. There's other ways of dealing with hash tables and collisions. There's double hashing, which is that if this first hash function leads to a collision, let's try a second hash function. There's also cuckoo hashing, which is that which is a strategy along the lines of, if my space is taken, I'm going to kick somebody out. I'm going to kick whoever's out of my space. So there's a lot of different strategies, and they all have different kind of good and bad things about them. Let me just check for 1 second. Laser, are you okay? Anurag? Laser, if you want to have raisins, you can go downstairs and have raisins with Mama in bed in a few minutes, okay? Sorry about that. All right, what is the worst case scenario for insertion and deletion algorithms in a binary search tree? So the idea behind a binary search tree is that you have n log n runtime. Sorry, that you have not n log n, you have log n runtime. Because if you're searching for an item, right, then what we've got is we've got roughly 50% on the left and you've got roughly 50% on the right. And so by going to the left or right, you are cutting your search space in half, right? So if I go to the right, then I've eliminated 50% of the items that I need to look through in the from my search space. I don't need to look at half the items anymore. And then I'll cut it down to 25, and then to 12.5, and to so on and so forth. Okay. So, and now, what do we need to? And so now, what is the? So that's our logarithmic runtime. Our worst case scenario, though, is what if we add stuff in a bad manner? So take the sentence, the quick brown dog jumps over the lazy fox, right? So QRST, the quick brown dog jumps over, the quick brown F the quick brown fox jumps over the lazy. So, and then dog. So there we go. The quick brown fox jumps over the lazy dog. Very famous sentence in the English. Why do we use that? Because it has every letter in the English language in it. Although it may not look like that because my handwriting is atrocious, terrible, bad, terabad. That is my handwriting. Okay.
You said every letter?
Yes. The quick brown fox
Oh.
jumps over. The quick brown fox jumps over the lazy dog. I'm just
That's
saying.
cool.
Yeah, it's so the so it's a famous sentence, but if we sort it, we notice there's something pretty terrible about this tree. The average run case of being log n assumes that it's going to be doing this over a balanced tree where it's split roughly 50-50, right? This one is clearly not split roughly 50-50. In fact, anytime if I'm trying to look for the word to see if the word mad exists in this tree, okay? Let's look through the search space. Okay, mad comes before the, so I've eliminated one item from my search space. Mad comes before quick. I've removed one item from my search space. Mad comes after brown. I've removed one item from my search space. Fox, it comes after fox, so I've removed fox and dog, then jumps, and then over. Sorry, it comes before over, and then before LM, then after L. Point being is that mad should be right over here. It's not. But to get there, I had to basically check every single one in every single word in here. This is an unbalanced tree. Basically, my search space is not being halved. It is a linear search time. I have to check every item. That is the worst case scenario. Or more to the point, let's go ahead and assume I'm adding 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth. This is no better than a linked list, right? It's just a linked list with extra steps. So, so our worst case scenario for a binary search tree, just a straight up binary search tree, is it is O of n to do anything with it. Now, in practice, that's in principle. In practice, that doesn't exist. Why? Because we're not using a binary search tree. We are using self-balancing binary search trees, which is chapter 9 in our textbook. But because of the sake of time, I don't really go over it. Because there's one chapter that had to get cut and that was it. But simply put, self-balancing binary search trees, there's things like red-black trees or AVL trees or or 2-3 trees, they each have strategies for ensuring that the trees remain balanced. And they all work out the principle that if you have a balanced tree, if a balanced tree becomes unbalanced as the result of one operation, it takes log n time to rebalance the tree. So if you had a balanced tree and now it's not balanced, it takes log n time to rebalance it. So worst case scenario for adding and removing in a self-balancing binary search tree, is log n plus log n time, which is log n. So, but those require extra code. Like the add method, I think is like somewhere of 50 lines for add if you're doing a red-black tree, which is the most student-friendly, I believe. All right. Any additional questions?
So, so what's the last answer?
Worst case,
Runtime for deletion. What was it?
Ulven. For add and remove, it's
Oh.
both Ulven. Because
Got it.
it's going to take that time, the amount of time to find it.
Yeah, I got one question.
Yes.
It's like the first part, number 4.
Yep.
You said it's stack. Could you explain, elaborate it?
So anytime that you want to do something for, so anytime you want to retrace your steps, having a stack is kind of the ideal, thing. Like when you're dealing with the maze, right? You want to keep a stack so that you have all your previous decisions and your most recent decision is at the top. And then you get rid of it if you need to backtrack. And then you can get rid of that one if you need to backtrack, and so on and so forth. I mean, you could technically argue that you could use a list, but a stack is much more better suited for this.
Yeah, that's what I wrote. List.
You could make an argument for a list because what is a stack but a dumb list? Right?
Yeah, now I get it.
But let me go. But so you'll have 4 questions like these on the exam, on the actual exam, but they will be multiple choice. So I'll be providing the answers, and I try to make my best to make them not conflict with one another.
Yep. Thank you.
Okay. Other questions? Right.
Oh, sorry, Professor. Like the last exam, will there be 7 questions or?
Oh, let me go ahead and I'll stop recording now.